everybody. And welcome to CITA seminar on a slightly odd time. Today we've got Erik, long last name, from the University of Alberta. And he's going to talk to us about the care and feeling of star-forming regions.
Thank you very much, Krista. And thanks to CITA and all of you for coming out. Since I'll probably forget to say it at the end, I'm really grateful for the chance to actually come and talk to you about some of the results that we've been getting. And I'm going to say that I kind of blew up this talk on Friday when I realized that there was a set of 2 or 3 different things I've been working on that could be sort of refactored into a different narrative. So if it's a little rough, I apologize. But I also have been told that there's going to be a lot of interruptions. So with that in mind, I'm going, feel free to interrupt and we'll make it look like it's all intentional. I gotta say that a lot of the work that I'm doing here is really transacting on the efforts of a lot of people. In particular, several excellent graduate students here called out in bold who are working on the BoCam Galactic Plane Survey team. And then my postdoctoral fellow Dario Colombo, also with Adam Ginsberg, sewed up the last part of the talk. And I usually start I start whatever talk I can with this picture, because this encapsulates what I like to study, which is this idea of a baryon cycling in the interstellar medium. And as an ISM specialist, I certainly regard stars as just a place you store baryons in between the times that they cycle through the ISM. But then we have this nice narrative that we tell in Astro 101 that stars then die and put their hot outer envelopes back into galaxies, into the atomic medium, which then somehow forms molecular clouds, and those molecular clouds host the next generation of star formation. In this talk, I'm going to be emphasizing the links between these phases. I'm going to start out by talking about a little bit of what we know and use that as the basis of an analogy for stuff that we see in later parts of the talk, namely emphasizing how molecular clouds feed star formation regions, and then some speculation on what we can infer about how the atomic gas feeds the molecular gas. To make up for the impending interruptions, I'm going to move a little quickly through the introduction, but feel free to interrupt. So this is a star form. Sorry? You don't get to interrupt. You can bother me later. No. So this is a star-forming region. This is Perseus, as seen in optical imaging. And we know it's a star-forming region because we see young stars. And therefore, they must have formed recently. And of course, when we look in the optical, what we see is messy dust, which we see here in extinction against the background light. And we have lately started exploring molecular clouds based not on the extinction of the dust, but through the thermal emission of the dust. And this is a thermal emission map of the same region taken by the Herschel Space Telescope. And what it's showing you is roughly the column density of molecular material along the lines of sight here. And what you can see is around the regions where we saw those stars forming, here, NGC 1333, these are the telephone numbers we give to these star-forming regions, we see that they're associated with high column density material. But I'm going to take and just note that this is a wonderful way of seeing the molecular cloud in an unbiased way. It's really quick. You can just scream across the sky and collect all this information. But because you're observing a continuum process, you have no information on the kinematics of what the gas is doing. But I'm going to change the same image and just drop down in brightness stretch to show off what this image looks like at low column density thresholds. And it's just a reminder that molecular clouds are a messy train wreck of turbulence and magnetic fields, and we're often describing them as filamentary. So they're characterized by these long aspect ratio structures of gas in them. And there's been a lot of push on this idea, given the Herschel work about the notion of these filaments and how they relate to the star formation process. I'm going to take the same molecular cloud and actually view it in another tracer and remind you of some of the other pieces in our toolkit. In addition to the in addition to the dust continuum observations, we also have molecular line observations. So here we're looking at specific quantum transitions of molecular tracers. Can't use H2 because it's invisible at ISM conditions, but we rely on other tracer species, and one of the most common is carbon monoxide. Now, this is the the J equals 1 to 0 rotational transition of carbon monoxide, and the combination of radiative transfer effects in chemistry mean that we tend to see this from about 10 to the 2 particle per cubic centimeter gas.
So how well dust traces gas?
Pretty well. We are more inclined to doubt our gas tracers than our dust tracers in the places where we think that might break down. But certainly everywhere that we can test in the diffuse cases, it seems to be pretty good. Factor of 2, I believe, was the number I heard bandied around today, and that's mostly observational. These data that I'm showing you are actually spectral line data cubes. So every pixel on the map that I just showed you is actually a spectrum. And it's a well-resolved spectrum. So we have several velocity resolution elements across this spectral line, giving us a nice profile and a great handle on the kinematics of the molecular gas. And we will often view these spectral line data cubes in the context of three-dimensional data structures. And we will look at structures in this position velocity data cube and kind of view the emission as a contour. And say we're going to contour the emission and look at regions above a certain brightness threshold. They'll be connected. And we want to then say, OK, well, this represents an object of some sort in PPV data space, and I can start to characterize it. So the language that I'll use takes these contours and then tends to put ellipsoidal approximations on top of them. And I'll characterize their sizes along the coordinate axes, or as the properties of an elliptical representation of a relatively complex structure. So for example, I'll give you the luminosities of these objects in a molecular line. So the carbon monoxide luminosity would just be the sum of emission contained within this contour. The line width would be given as a moment over the spectral dimension weighted by the intensity. And this would give us an estimate of the kinematics, or say the kinetic energy inside a molecular cloud contour. And I'll focus on these scalar properties. The radius would just be the size and the size estimate in the spatial direction. The line width is in the spectral dimension. The luminosity is just the amount of light. Typically, with molecular clouds and CO, we will scale it to a mass using a constant mass to light ratio. This is known to be inaccurate in places, but to a factor of 2 is pretty good if you confine yourself to specific regions on large scales. And I'll also discuss a bit the notion of this varioparameter, which is functionally a ratio of the kinetic energy to the gravitational potential energy. And it has the sense that alpha equals 2 is the dividing line between stuff that is unbound at alpha greater than 2 and stuff that is bound at alpha less than 2. So
What are you using for your radius if you have something which isn't
not a sphere? So you calculate the spatial moment, basically the dispersion, and then you average over a bunch of potential density profiles, and you put a numerical prefactor on the Gaussian width of that.
One second, are we talking about PPV cube or 3D space?
This is in the PPV cube, yeah. So, but we consider the spatial extent of one of these.
Convert V into R.
Oh, sorry, no, it's in the cube, but it's only the the spatial dimensions. The spectral dimension gives you the line width, yeah. So the number that we whack on the front of the radius to convert essentially the second moment in space to the radius has been kind of calibrated for spherical profiles over a range of density distributions to give you a number that works for centrally concentrated emission distributions. It is a knob. So if I say 2, that could be 1.7, it could be 2.3, 2.4 really easily. We have chosen a number based on back compatibility with the literature rather than something really drawn from deep in the depths of physics. The final thing in the introduction, I guess 2 more points I want to make on the introductory points. First is we have a molecular line toolkit. And by changing the species that I'm observing, I actually can probe different regions within the molecular cloud, different chemistries, and different physical regimes. For example, this is a map of the same region in 13CO, so a rarer species of carbon monoxide. And it sees a little deeper into the cloud up to higher densities. And this gives us a chance to kind of peel back the density hierarchy of the cloud in 3-dimensional space and look further in there to infer cloud properties. The last thing is a bit of vocabulary, which is, if I look at this region, I'll often describe the whole area as a cloud. I'll talk about the regions that are forming clusters as clumps, and individual star-forming region, or individual objects that form individual stellar systems are cores. Cores are reasonably well defined, or how about the best defined of the objects in this hierarchy. The rest of the definitions are a little loose. It is a continuous hierarchy all the way down from galactic disk scales down to stellar cores. And we use the transition from atomic to molecular gas often as a boundary for a cloud. This breaks down, say, in galactic centers. And then clumps are somewhat poorly defined, but I will use those to sort of represent compact, bright features of emission that come out of the observations. And those have the right size and mass scales to be cluster-forming objects. But if you're going to back me in the corner and ask me to define these things, I'm going to throw down my ninja smoke grenade and run out the door. Why should you care? You have to remember that everything that I'm going to be talking about today represents a model for the subgrid physics that we put into our understanding of the evolution of the universe. If we want to model galaxy dynamics and evolution over a Hubble time, you need to inject star formation and a model for star formation into what galaxies do. It is a driving agent for galaxy evolution. And a lot of our models are built on this idea that we have an ensemble of molecular structures that go on and form stars. We want to come up with a model for how much stars per unit time are produced from these molecular cloud populations. And the evidence that I hope to get to at the end is making an argument that there are some additional correlations built into the cloud population that we should be taking into account when we're understanding our subgrid physics for galaxy evolution. Now, star formation is ultimately the process of falling down. It is gravity pulling material together into a centrally condensed object. And I yanked this particular schematic off the JWST website. And it's an argument, or it's just laying out how low mass star formation works. And the first step in the diagram is, of course, the collapse of a molecular cloud core to form a stellar system. There's all kinds of exciting stuff that happens in these later panels, but I just want to start out here and work up to higher scales because fundamentally the act of a core collapsing to form a star, thanks to the JWST slide, says it takes about a mega year to get down to these small scales, and stars are, for lack of a better reference, about a solar mass. So you get about a solar mass per mega year flowing into the stellar population through this process of star formation. And we see excellent evidence for this out there. This is just one of many results. It's a cute recent result that came out. This is the protostellar core B335. These are results out of ALMA. And this is a dust continuum map showing you where the material is along the line of sight. But the nice thing about ALMA, especially at this 345 gigahertz waveband, is you can also look at molecular lines at the same time. And in making this map, these are two separate species in two separate regions. The columns are different regions in the cube. And it shows you this characteristic infall profile for these spectral lines. So this is the profile you get when a spherical collapse sort of falls down into the middle, and you get this characteristic line structure here. And the point of this is the black is showing you the observational data, and then the red is showing you a relatively simple model for this spherical collapse. And it is such a well-established phenomenon that there was an annual review showing essentially this exact line model in 1999. And I like this schematic because it just points out that this really does depend on the specific profile of the velocity of collapse as these objects sort of fall in towards the center. And the line profile is kind of flipped in that the middle represents the outside of the core, and then as you get out to the wings, those are closer and closer to the center. The other thing the model gives you is this blue-red asymmetry based on the excitation conditions within the molecular core during its collapse. So not only is this model sort of well-tested in literature, we really do see the act of things falling down. Though I imagine this audience doesn't need to be convinced that stars form.
Why is it in the real data, central value always goes to 0, while in your quantitative model it doesn't?
The surface brightness, I think that it does go a little below 0. Here. I mean, this is a single continuum, so it's slightly absorbed with respect, I guess, to the CMB at that point. Yeah. Or I guess it's relative to the continuum, because this is sitting on top of a bright continuum source. All right. So with that as kind of the small-scale foundation, I want to start presenting some of the work that I've been involved in and other things that have been going on in literature that talk about how we get from those clouds dumping down to form these cores. And one of the sort of best, I guess, relatively early treatments of this idea of sort of material flowing along these filamentary structures came from this study of the Serpent's south core. Were you on this paper too, Rachel? No, okay, I can't remember. I know that Helen Kirk did a lot of the leading work on that, but what happens in here is that this is a dust continuum filament seen here, and the blue here is a region that they have done spectral line observations over this filament. So if you look at that, you see this nice filamentary structure, and then the colored symbols indicate the protostars that are being found along this filament. So there's clearly stars forming in this region, and there's a bright central concentration of material. And the velocity, this is now showing the velocity centroid. So this is the line of sight velocity of the material sort of moving towards you, away and towards, to give you this nice gradient along the filament. And the sense of it is such that it's sort of falling down in towards the center. So gradients mean a lot in astrophysics. But in this case, they sort of scratched their heads pretty hard and came up with the idea that, OK, this is consistent with material sort of accelerating in towards the middle of this filament and building up. Well, in this case, they made the argument based on the geometry of the filament, arguing that this is probably not a disk seen edge-on, given sort of the column densities of the material involved. and I guess not seeing a rotation curve. Sorry?
You don't have to be a distant rotate.
No, but I mean, this could be basically shear, but the other kind of piece that they were putting in is also that they can do this infall studying through the lines to kind of watch things falling onto the filament radially along the line of sight. And so the lines are giving you this nice infall model on top of the materials who are falling down. So there's this idea that that you can then map that gradient, map the gradient and the infall profile to constrain sort of how quickly material is falling onto the filament and then sort of flowing down into the middle. So there was this nice piece of additional observational evidence there, and it gives us these mass rates that are feeding, hundreds of stars.
In the previous infall asymmetry plot that you showed,
Yeah.
you relied upon a gradient in excitation temperature to be hotter anyways.
Yeah.
You get that. When you're accreting onto a filament, it's not so clear that you would have that gradient in excitation temperature.
Well, the excitation can be boosted up through increasing the density. And I guess, I don't recall. HNC does have a pretty high critical density here. So that's a case where being essentially dense region would give you a gradient in the excitation, just from more collisions, bumping it up. One of the projects that I was involved in also looked at this Serpens region, but it looked at it in this, so here's that central concentration. It looked at it using an interferometer, the Karma interferometer, looking at this molecule N2H+, and produced a higher resolution map over a smaller region. And this feature showed a couple other filaments. So here's that main filament here. But what was that was sort of seen before. But we also saw this smaller filament, and this is the intensity map here. This particular map shows you the velocity centroid surface for that. And in addition to there being a relatively weak gradient across the filament, what was kind of novel about this is that there was a relatively sharp gradient perpendicular to the direction of the filament. And in the case of there being purely radial collapse, you shouldn't get that if it's just gravity doing that. So one of the ideas that was sort of kicked around by the theory side of this collaboration is that this can only happen if there's a magnetically mediated collapse, where you have kind of a layer of broader material that then is sort of flowing in the directions dictated by the magnetic field, and it's sort of seen obliquely so that material then is kind of accelerating and crashing onto this filament here. So you need to kind of break the azimuthal degeneracy somehow, and this magnetized layer undergoing gravitational collapse will give you a model that can produce both the gradients along and also perpendicular to the filament.
Just backing up, how do they you break the inflow versus outflow symmetry?
So in the classic case, singular isothermal sphere, that comes from the excitation gradient.
I can see it.
Yeah.
Dense object.
Yeah. But I mean, in this case,
In a large scale thing like that, the arrows going that way,
yeah.
which are based on radial velocity, which will be blue or red shifted depending on how that cloud is tilted relative to
Right. I mean, in this case, we have definitely taken the argument that, we don't have the line of sight information in this case, and we can't leverage the gradient of the excitation temperature. So we have interpreted this in the context of the broader study as kind of an initial condition and assumed that the gradients were oriented in the directions that Kirk et al. Argued, and just sort of said, now we're seeing this at higher resolution. So we paged it backwards, but in isolation, we don't have that from this particular study.
And was the evidence large-scale flow or more concentrated on, say, flow locally onto the high-density region of filament?
So theirs were definitely, they had sort of two arguments in there. One was the concentration onto the ridges, and then the flow down the ridges. The concentration onto the ridges was something that there is well backed by the infall profile, and then the flow along the filament is an argument that they've made based on the geometry and stability of the filament.
It's a plausibility argument, I guess.
Yeah, it is. The collapse onto the filament has fewer bells and whistles, has fewer knobs than the flow down the filament argument. All right. So this is a nice picture that we can lay out because we do see lots and lots of structures throughout the Milky Way that have been studied on a case-by-case basis, and people have made arguments about every special case, and like, oh, this case is this is an infall feature. We look at the velocity gradients here. So there's been a lot of sort of precious snowflakes that people have studied in great detail and come up with a nice story about. And there's pictures like this, which are pretty nice because we see this nice ridge here, and then there's these fainter structures that are sort of oriented perpendicular to this. And you can say, well, this seems like there's a good, broad scale magnetic field is in this direction. You get that from stellar polarization. And so you could say, you can tell a story that works well where the material flows down the field and then kind of crashes into these broader, or into these brighter structures. Then those structures collapse under gravity to form stars. So it's a nice story, but the concerns I have about it are everybody tells a story about an object, and it's a good story. But how does this hold up kind of in a population-based sense?
What is the temperature influence?
Sorry, temperature? 10 to 20 Kelvin for the bright ones. Here, I don't know that we have good temperatures that are actually gas. We have dust temperatures, but that's not kinematics. Yeah, I mean, molecular line cooling is incredibly strong and fast. All right, so to answer the question of, well, ask this question, how important are these filaments for forming stars and star formation? And part of the question that you have to address is, well, how many filaments are there? There's all these regions around us. They have different filamentary structure. And I tasked, as an undergraduate student at the time, and now he works for me as a graduate student, Erik, to come up with a new approach to trying to identify filaments within an image. And this is the outcome of the approach that he used. He developed this algorithm called FilFinder, which is based on mathematical morphology, which is a corner of computer vision. And there's many, many different filament finding algorithms operating right now in the field. What this one is good at is finding the full network of filaments, and perhaps maybe even a little aggressive with some of these branches. But you can prune those down using his method and pull out both the bright filaments, but also it's sensitive to these striations, the fainter filaments here. And I asked the question, well, okay, go and run this on all of the infrared maps that we have from local clouds, and do clouds with more filamentary structure or more pronounced filamentary structure show higher rates of star formation? And the answer is maybe. The x-axis of this plot shows the median brightness of a filamentary network above the background of sort of a smooth cloud. And it's on a logarithmic scale. On the vertical axis is the star formation rate per unit surface area in these clouds. And as long as you don't look at that point, you could kind of convince yourself that maybe there's a trend here anchored by, okay, here's, Aquila and Orion and such are up here, and then you get down to that case. But then there's Chameleon up here. So it's huge star formation rate per unit area, which seems to suggest that this can't tell the whole picture. And the story that we can tell to explain this away is to say, well, Chameleon's at a special time in its life. It's at the end of this filament feeding process. But once you start doing that, you have to fold time into your picture. You have to start to account for the scatter between these points, and that scatter has to be driven by time evolution of the systems. And then you're in a case where 14 points is not enough. You can't do good population statistics with 14. So we are in the case where we need to start to explore things broader in a more sophisticated fashion over a wider population. And we have to let go of this filamentary mediated formation because our resolution, we've just run out of objects that we can do the imaging on. So we can ask the question then, well, what is the rate that mass is going to be flowing into these clumps sort of broadly? Just lay it down and say how much material is flowing into clumps. Doesn't matter how I do it. And to do that, I need a good population of clumps. And that comes out of this study, the BoCam Galactic Plane Survey. This is actually one of the first galactic plane surveys in the millimeter continuum. It was taken by the BoCam instrument on the Caltech submillimeter observatory, and it's operating at a 1.1 millimeter wavelength. And this is a typical BoCam image. Well, maybe not typical. The sky is pretty blank if you are observing it at these wavelengths from the ground. But we do see some structures in here. And my job was to kind of come up with a description of where those objects could be described as isolated regions and kind of pull out a catalog. It's not necessarily saying that these are real physical objects. I just say that this is a reasonable reduction of the image to a set of sources. And then we can go and look at what those sources are. And one of the ways we got a handle on what those sources are was through spectroscopy. This is some ammonia spectroscopy that we did. And critically, what this gives you is it gives you a line of sight velocity. All this other structure is the hyperfine structure of the ammonia line, so it's not like there's 5 clouds along the line of sight. But this particular line tells us both how broad the line is and where it is along, how it is moving along the line of sight. And that is critical because I can use that line of sight velocity and drop down these BoCam emission features onto the galactic rotation field. With the galactic rotation field, I can resolve where those objects are along the line of sight, because we say all of this motion is coming from the projection of galactic rotation along the line of sight. But this leads to a distance degeneracy. We don't know whether it's on sort of the near side of the galaxy or the far side of the galaxy with the same projection onto the line of sight. So we need somehow to resolve this to figure out where they are. For the initial work that we did, we spent a lot of time kind of grinding on, let's throw away most of the sources and only come up with those that we can, for example, find self-absorption features that would say this is clearly near side, or other associations that would say it's far side. And the upshot of it is that we are seeing these things that we would call clumps. If we look at the masses of these clumps and their dynamical state, we find that they tend to sit around 10 to the 2 to 10 to the 4 solar masses. And they tend to sit in this sort of wide range of dynamical states down to fairly disturbingly low virial parameters. These are strongly self-gravitating, probably collapsing objects. Up here, these would be relatively stable objects if this is a good description of their energetics. And then stellar cores would usually live right here in this space. So we're seeing the regions on average that are going to go on and form large stellar clusters as opposed to individual stars.
Sorry, were you using this information to break the distance?
No, we broke it first through basically a lot of homework and sort of, making grad students cry and say, well, where is this? And they had to think pretty hard. So every point on here was hard earned. But there's got to be a better way.
What's your confidence in that determination?
For these, there's probably about a 10% error rate. Yeah, our grad students cried a lot, but they did great work. But there does have to be a better way. And so we said, enough grad student tears. Let's try to come up with this project that we called grandly the distance omnibus, which is instead of saying we're going to resolve this as near far and use that as the distance, we're going to treat the distance as a Bayesian random variable. And we're going to use all of the data we can. We're just going to kitchen sink this, throw everything we have at it, and figure out what the posterior distribution of distances associated with a bright source is going to be. And those that have relatively narrow, credible intervals for their distance are things that have a well-determined distance. And other stuff, well, you have at least a PDF of distances, and you can then Monte Carlo over it to come up with population statistics. So it's not too bad. And we grabbed a bunch of, our kitchen sink had a lot of things in it. It had the presence of infrared dark cloud emission would give you not necessarily an object on the near side, but when combined with a model of the infrared luminosity of the galaxy, it could come up with where an object was along the line of sight. We were able to pull out spectroscopy from a bunch of different lines, not just the places where we pointed the telescope, thanks to some wide area, low density molecular surveys. We tied known objects to certain elements in our data set and made a way of associating H2 regions and stellar clusters that are at known distances with our sources. We were able to pull out the parallax distances from water masers that are being undertaken by the Bessel project and just dump this all in and aggregate all of this into a bunch of distance posterior distributions. And we come up with, this number is, overly precise for what it is, 1,700 sources that we feel like we have good narrow distance intervals for. And we can drop those down onto the galaxy. So these are the points as we sort of observe them in the galaxy. And part of this is our survey sampling strategy and the data that we can actually put things like we depend on everything in the kitchen sink, not just the BoCam galactic plane survey. So those are subject to sampling, like where did Bessel look at their data. We also have kiloparsec scale error bars, if you will, on these distances. But we start to pick out some of the spiral structure. And the artist's rendition of what our Milky Way looks like in the background really is the, it is drawn from the ensemble of these data. So remember, the thing in the back is made up, and the thing in the front is the kinds of data that we have to deal with.
But at some level, you do have the spiral structure of the galaxy as a prior on where you...
Yeah, and if you say, well, all of these readings are associated with spiral structure, that's great. And I guess the Bessel project has basically put out a distance model now that asserts that these things are consistent. We don't make that guarantee, but we could throw in. There were fights.
Well, there's certainly evidence for non-superficial.
That's actually a bigger effect than the arm interarm here, and we were relying, like Bessel has been tuning the presence of non-circular motions in their galactic structure model on and off. So we're, in some sense, we had to freeze to one version to make this set of distances. But as they evolve their distances to new, or their model, we can feed it in again and take into account the non-circular motions.
What are the yellow dots versus?
The yellow dots are the parallax sources, and the black dots are everything else. Sorry? Well, the problem with the Gaia is that it's stars, right? And these are not. So, anchoring that is you have to scratch your head about that. There are ways that you can work through it and just say, well, you look for basically distance versus extinction kinds of curves, but with really good distances to the stars, and then you can work out where that's going to be. The problem is that some of the most exciting stuff here are also in the most heavily extinguished regions in the field, and thus you're not going to really crack open molecular medium, because that's exactly where extinction is.
In the other galaxy there in Perseus, what are those black fingers?
Those where we did specific fields in the BoCam Galactic Plane survey. So the continuous coverage is kind of in this range, and then we did, this was an exciting place, and this was an exciting place.
But you have to believe that stuff is spread out that thickly
I
along.
get a kiloparsec error bar. I mean, yeah, so my uncertainties are a kiloparsec-ish.
So there's nothing in the Bayesian analysis that gets friends of among BoCam sources.
No, we don't assert gregariousness. Yeah, the point is to come up with a PDF. If that PDF is broad, that's okay, because we're going to then marginalize over it. The criminal sin is making your PDF too narrow.
So would you take the median distance as a good estimate?
We use the peak probability as the estimate, and then the sort of interval around it to get down to, I think it's 90% confidence is the error bar. And sometimes that range is 12 kiloparsecs. It's just poorly constrained, but it's a big PDF. All right, so one of the things we can do is then take these clumps, we know where they are, and then we can tie the clumps to what they look like in terms of star formation. So the star formation indicators we look at are things like the 70 micron emission in the infrared. So that's warm dust. We have 24 microns. That's very hot, small grain kind of dust, and some PAH features. Water and methanol masers are high mass star formation indicators. And then finally, ultra-compact H2 regions show up as an indication that really there is high mass star formation going on right now in these regions. And these are listed kind of in order of an evolutionary sequence. And we can go ahead and sort of make a list of what the clumps look like based on the most advanced star formation indicator that these sources have. And this ordering is all the star formation indicators that we've written down, and we've ranked it basically in order the cases where, for example, water masers tend to have all the other sources, all the other indicators above it, but they don't tend to have methanol masers or ultra-compact H2 regions. But ultra-compact H2 regions tend to have all of these other indicators. I guess, there. So what we have here is sort of models of evolutionary sequences of these clumps, and then we have things that have none of these indicators here. And this is plotted as number distributions as a function of flux density. The dark gray bins are places where we have good distance indicators. The light gray bins are places where we have taken the rest of our sources and inferred distances based on proximity in PPV space to those sources. So these are a lot less well understood distances. So these are the ones that are measured. These are imputed through the method that was adopted in this paper by Brian Svoboda, Yancey Shirley, and the rest of the team.
What do the protostellar 70 micron unique and mid-IR labels mean?
So the protostellar is all these. 70 micron means it's 70 microns and nothing else. And then mid-infrared is the 24 and 70 and or 70. So we saw that there was sort of, given the correspondences between these two boxes, you sort of saw the cases where the 24 micron showed up, appeared all the places that the 70 showed up, but 70 without the 24 is what's here.
Did you, maybe you're going to show, did you work out volumetric luminosities and thermal dust temperatures? And things?
Yes, yes, but I'm not going to show it.
Is there a progression?
Yeah, so,
Luminosity and
right. Yeah, I'm going to emphasize mass. But this mass is then marginalized over a distribution of dust temperatures and gas temperatures, all the distances for the sources and everything. And we've made tons of this style plots, but for this purpose, I wanted to emphasize the mass. There is basically a trend with all of these, as we proceed from less evolved to more evolved, we really do see an increase in pretty much every quantity you think of. Temperature, they get hotter, they get more massive, they get a little more dense, but not a lot more dense, volume density, and so forth. The Viru parameter is basically the same for them as they go through. We don't have tons of kinematics on all this. That's a statement I'm making based on having looked at a smaller sample. Since we don't have resolved line observations of all of these, we can't say that in this beautiful style analysis. But you tend not to see things that have Viru parameters larger than 10 or less than 0.1, in part because of observational biases. Cool.
But the thing that has an ultra-compact H2 region now, are you saying it was less massive before?
So,
or are you just saying that it takes a massive guy to form an ultra-compact H2 region?
so the thing that we see is we don't see the clumps that are going to have the same mass as what hosts ultra-compact H2 regions now, but are starless.
Yeah.
And this is an observational thing that was sort of stated less generally, which is, where are the progenitors for the things that are going to form 10,000 solar mass clusters? And there's two answers. They're massive, and so they should have high densities and therefore short freefall times. So we're temporally selected against seeing them. Or there's feeding. And you start with a low mass clump, and you make a high mass clump.
Even in the first place, they had to come from somewhere.
Yeah.
They could have been massive and short-lived forever.
No. And so the contention of this paper is that the answer is C, all of the above, in that we can measure the densities of the objects as we proceed, but we also do see evidence for a population-wide growth in mass of these objects as you proceed down the evolutionary indicator. They move to, like, starless objects are systematically less massive than protostellar objects. Things that host ultra-compact H2 regions are systematically more massive than any other subpopulation here. So it's a nice estimate, or it's a nice result because it covers the whole population sort of epidemiologically, and it argues over the whole population, you need to feed a clump at about 100 solar masses per year, even factoring in the idea that high mass objects have a shorter lifetime through free fall, because we can measure the volume densities of them. All right.
So in this scenario, you're forming low mass stars before you form high mass stars. Is that generally true?
I don't know that I can say that for sure.
Depends on when you get this. There's indications of high mass star formation without, or whether you form the high mass stars without having those indications.
Right. But if you're feeding in that much material, it's probably less.
All right. I'm at the end of my allotted time, so I'm going to give you a brief commercial for part 3. But I'm not going to give you part 3, which is to ask the question, is there evidence for this process, mass flows on even larger scales? I'll say that the problem is we don't have a good population of molecular clouds in the inner galaxy until now. So what we did is we took an ultra-high resolution survey of the galactic plane. This is the new resolution. This is the old resolution. This is the effective sampling of the old resolution. And we did some truly mind-bending image processing to pull this out, or object cataloging, using some glorious, simply glorious things. And whoop, this is the plot I wanted to show. We get 14,000 objects through the galactic plane. We tag every one of them with distances or kind of imputed distances. And we say, well, how massive are these molecular clouds? And we ask, how quickly are they forming stars? Because we have infrared surveys across there, and we can tag each one with a star formation rate. Historically, we've kind of treated the organization of the molecular medium as being something you don't have to worry about. A solar mass of molecular material is going to form stars at the same rate pretty much no matter where it is in the galaxy. But when we make these observations, the masses of the clouds seem to be important, and that this is the ratio of the infrared luminosity relative to the CO mass. So this is basically star formation rate relative to the molecular mass versus the molecular mass. And what we see are the highest mass clouds also are the ones that have the highest star formation rates per unit molecular mass. We don't see trends with, for example, free fall time or, we don't see obvious trends that say these are really more dense and so they should be forming stars more rapidly. But it really seems like the formation of these larger high mass clouds are things that are forming stars more efficiently. It's a terrible terminology. Formally, they have shorter molecular gas depletion times.
So, are you sure this isn't an effect of only the large things can have high mass stellar clusters, and therefore those things are intrinsically IR bright, and therefore you infer a high LIR to MCO?
Right, but that's not built into the models, effectively. Because the standard models are, it just depends on Mach number, this is the distribution that comes out. It doesn't, you sample randomly from the cluster mass function.
The ratio is the star formation rate per mass, that's the luminosity per mass.
Right. I mean, so this is calibrated on the size of clusters, right? So, I mean, you're right that the infrared, this relationship breaks down at this level, is where it dies. But above it, we trust the ratio to trace this formation.
Masses of stars, and you're sampling them in a random way, then you can trust the correlation pretty well.
Yeah.
But you have to, I'm just wondering about the stars.
About the star formation rate indicator? Yeah. I mean, so this is basically repeating the analysis that was done in the 80s, but with better data. And huge scatter, but they were just basically flat because they had huge scatter. And I say that there's huge scatter, even worse over here, and we see a trend. And we see that it depends on where you are as a cloud mass.
Well, if massive stars were contributing more at higher molecular cloud masses, would you expect to see an increase in dispersion, not a decrease?
In dispersion?
Yeah.
I mean, you may just be
Depending on that situation on a few objects.
right.
Not
And-
up until it's 6.
Yeah.
Because once you've got more than about 2 to the 4 solar masses of stars,
Yeah.
Well, it's 10 to the 4 solar masses of CO.
This is gas, yeah. So up here is what you're saying. This is a full sampling of the IMF. You're going to get there. Stochastic sampling is going to become important here. And so sure, you can have dispersions. This is also where distance assignments fall apart, and our ability to pull the infrared luminosity out of the background falls apart. So here, this is observational error. All of those effects should get smaller as you move here.
Do we know that the luminosity function on the behavior of itself is independent of the molecular cloud mass?
The luminosity function.
Form parts of the luminosity function that will small clouds.
We don't know that as well as we should. So that's my contention. I mean, all of this stuff is done population-based. All right. So that is the commercial for some exciting work that's coming out.
Just before you put that one on,
Oh, too bad. No, go ahead.
the thing that's called MCO, is that mass of the gas from CO?
Yep.
Not out of CO.
That's the mass of the gas from CO. Constant mass to light ratio. I will note that if you get the CO mass conversion wrong, that moves things perpendicular here, right? So it can't give you this trend.
Well, F over M is 1, even in the diffuse interstellar medium. It's just magic.
Magic?
Yeah. Well, I mean, that's just the way it turns out. The
Yeah.
radiation field is that strong.
Mhm.
That's how it comes out.
Hooray! Got that.
But that's off your block.
Yeah. All right. So, point here, just to conclude, is we see this mass accretion on a wide range of scales from individual stars to evidence even at the cloud scale of things constantly building up. And a lot of our models don't include the scatter and the time evolution as things sort of proceed through this conveyor belt of mass. So I think that we can start to revisit the organization and the feeding of the star formation process at a variety of scales, thanks to some new observations and methods that we can address this on a population basis rather than on a case-by-case basis. I know people got to go, so I'm happy to stick around and talk indefinitely. But until then, see ya.